Right, so I'm planning to start today by just going over the answers to that math quiz so you can compare your thinking on that. Um, Anybody who wasn't here, I know you weren't here, it was just sort of, it's not really a quiz. It doesn't go into your brain or anything, but it's just a way to make sure that you're in the right place with your knowledge of math and stuff like that. And then I'm going to start out with a pretty detailed outline of what we're going to do in this class. I'm going to try to, as we go through the class, keep bringing up this outline. And just sort of try to keep you aware of kind of where we are in the whole process of physics, physics 1. So starting with this long outline probably means that I won't be able to give you a homework assignment over the weekend, but that's how it goes sometimes. So, and then we'll get to actual like calculations and stuff like that probably. Well, I guess it would be Wednesday for you guys. That's more good news. All right, so first of all, let's go through the answers to that math quiz. The first question, the first problem was to plot the function y equals x squared. Some of you might, recognize that's a parabola, and you might just be able to plot it without doing any, plugging in any numbers or anything. But you could also do it by choosing a few values of x and plugging them in, plotting points until you get a feel for what it looks like. This is a really important function in physics because, because anytime you have constant acceleration, which comes up pretty often in this class, a position versus time graph is a form of this. So we'll see this shape a lot. But what the function looks like if that's the horizontal is the x-axis and the vertical is the y-axis, then this is a parabola that looks something like that. The second problem was we want to calculate the slope of the line that goes through, and I gave 2 points. One was the point 1, 2, and the second point was 4, 3. So if I plot these 2 points, if this is x and this is y, it looks something like, the point 1, 2 is somewhere around there. You go 1 along the x-axis and 2 up the y-axis. And the point 4, 3 is somewhere like here. And so we're talking about calculating the slope of the line between those 2 points. And the slope, you might have heard it described as rise over run, or you might have heard it described as the change in the y value over the change in the x value. Those mean the same thing. And you can actually calculate it. You can say the change in y value and the change in the x no like automatic starting point or anything. You'll get the same answer either way. But the way I'm going to do it is I'm going to start at this point, and this is going to be my destination point. So the change in y, it starts out with a y value of 2 and ends with a y value of 3. So the difference, the change, is 3 minus 2. Okay. And then the change in the x value, x starts at 1 and ends at 4. So this is going to be 4 minus 1. And so the numerator of that fraction is positive 1. The denominator is positive 3. And so the slope here is 1/3. And if I would have called this the starting point and this the ending point, these two would have just been switched. These two would have been switched. So we would have had -1 over -3. The negatives cancel and you get the same answer. Please stop me if you have any questions about any of these. Number 3, we started out with a times b squared times c squared over b to the 4th times a times the square root of c. And I guess I'm going to rewrite this as a times b squared times c squared over b to the 4th times a. And then the square root of c, we can also write that as a c with an exponent. What's the exponent that represents the square root? 1/2, yep. So this is c to the 1/2. And now the easiest way to do this, I mean, there's a couple ways to do it, but the quickest is if you remember the exponent rules. Well, first, we have an a here and an a here, and those cancel. So that's easy. The a's are gone. But now if you have b squared divided by b to the 4th, that's just b to the power of 2 minus 4. And so we can write the b squared over b to the 4th is just b to the minus 2. And then do the same thing with c. C squared divided by c to the 1/2 is c to the power of 2 minus 1/2. And so we can just write this as c to the 3/2. And there are a few ways to write this. That's not clearly the obvious solution to this unless I give rules for how I want it simplified. But this was just sort of a problem in dealing with exponents. Yes. Mm-hmm. Or a lot of people would write it as c to the c cubed square root over b squared, something like that. Number 4. So we have this expression. We want to solve it for a. And the expression I gave was a squared times b times c is equal to 4c plus b squared times c squared. Well, we want to solve for a, so we want to get a by itself. So first I'm going to get a squared by itself. So we have a squared is equal to all of this stuff divided by the quantity BC. And now we can take the square root of both sides. A is equal to the square root of all this. And one more thing, if we know A squared is equal to this, well, there's two ways that you can get this when you square something. Your answer could be the positive square root of this thing, or it could be the negative square root of that thing. So yeah, you need that plus or minus in there. And, you know, this is algebraically a trickier kind of problem like this than you're going to see most of the time. But in physics, you know, in a way, doing this kind of problem with physics is sort of nice, I think, because at least for me, like I remember when I was taking whatever class it was where I first learned about the plus or minus, and I kind of vaguely understood, you know, like, okay, yeah, you square a negative number, you get a positive number. But in physics, we're going to see that we're going to have answers that have two solutions like that, a positive and a negative. And both of those two solutions are always going to mean something physical. And the way, since you always want one answer, in physics, in our class anyways, we're going to want one answer. You're going to always have to come up with a reason physically that you're going to choose either the positive or the negative version of that. So this plus or minus thing is going to come up quite a bit. And then the last one was to solve this system of equations. And the equations, we had x1 plus x2 is equal to 50. And then the second equation said negative 2x1 minus 3x2 is equal to negative 10. There are a few ways to solve problems like this. The first thing you have to notice is for this to have a solution, to be guaranteed that this has a solution, you need to have the same number of variables that you have equations. And these equations can't be disguised versions of each other. Like if this second equation said negative 2x1 minus 2x2 is equal to negative 100, it looks like its own equation until you realize that that's just multiplying negative 2 times every one of these things. And so those are really like disguised equations. And if they're, in other words, they're really giving you the same information. And if you have two variables, but only one equation worth of information, you can't do it. But these are not, don't give the same information. So we have two equations for two variables, and we can solve this. Yep. Yeah, so there's a couple ways you can do it, but substitution always works. So when in doubt, just do that. So I'm going to use this one, the first equation, to solve for x1. So x1 is equal to 50 minus x2. And then I'm going to plug that into the second equation. So now we have negative 2 times this thing that we know x1 is equal to now. So negative 2 times the quantity 50 minus x2. Minus 3x2 is equal to negative 10. And now we have a single equation with a single variable, so we know we can solve that. So let's see, this says negative 100 plus 2x2 minus 3x2 is equal to negative 10. And so we get negative x2 is equal to, maybe I shouldn't do so many steps at once, but I'm combining these two things, and I'm adding 100 to both sides to get the 100 over there. And so this is equal to 90. What did I do wrong here? I don't remember that answer. What did I do wrong? Oh, on the in this is the system I gave you, right? Or not? Okay. Well. Oh yeah, I think right. I didn't have the. I just wrote it differently the two times. So, anybody remember? Did I have? Can you look in your notes? Did I have that -2 in the second equation there? Oh, okay. Okay, so that's the problem. Okay, so this is that, and now let me redo all this. So we have 100 minus 2x2 minus 3x2. And so now this is negative 5x2 is equal to negative 110. And so x2 is equal to 22. And you have to solve, so we have one of the two variables, but we're not done until we have values for both of those. So plug 22 in for x2, and you get that x1 is equal to 28. Any questions about that? Okay, so like I said, if this all just looks totally foreign, come talk to me about it. You know, otherwise, that's about the kind of limit of the difficulty of algebra that we're going to have in this class. All right, so now let's go into an outline of topics for this class, sort of the flow of how this is all going to go together. So an outline of College Physics 1. I'm going to start out with units, unit conversions, and scientific notation. Anything that you measure has units attached to it. Like if you measure the width of this room, you have to decide whether you're going to do it in inches or meters or whatever. And we're going to need to go back and forth between different types of units. So we're going to first talk about how all of the units that we're going to deal with in this class come from combinations of 3 basic unit types. And those are units for length, time, and mass. Those wouldn't have to be your 3 basic units, but that's what we're going to use. So there are a lot of other things you can measure, like speed, for example. but the units for speed are the units of length divided by the units of time. So every unit that we're going to use is a combination of those three. And the kind of stuff that we're going to want to convert is, like, for example, how many feet per minute squared are there in 10 meters per second squared. You know, some people are going to use some kind of units. Other people measuring stuff are going to use different units. You need ways to go back and forth between things that, like, similar quantities, the same quantities. So notice what's important here, and this is always going to be true if you're going to convert one unit type to another. They have to have the same basic meaning. So notice that this is units of length divided by units of time squared, just like that is. So there's no way to convert from feet per minute squared to like a distance measurement, you know, to inches or something. They're not the same thing. Okay, that was too long-winded. We'll get to that more later. But well, we'll get to the long-winded part in time anyways. I just want to give you sort of a layout of it. So that's okay. I'm going to correct that on my second one. So after we're done talking about units and conversions, we're going to get into what you can think of as really the first physics topic, and that is one-dimensional particle kinematics. So particle means essentially that we're not worried about changes in orientation. So, like, if you're doing measurements related to particles, you're perfectly happy getting an answer. Like, okay, so if you're treating me as a particle, okay, then at the end of the calculation, I could be facing this way, or I could be facing this way, and the answer is going to be the same. Okay, if we care about changes in orientation, we can't treat the thing as a particle in our mathematical analysis. So later on, at the end of the class, we'll talk about how to take change in orientation into account. So that's the particle part. The kinematics part is that we're only describing motion. So describe the motion without thinking about the causes of the motion. So no causes of motion are considered. And when I talk about causes of motion, I'm talking about, like, forces applied to things or energy that the thing has. We don't know anything about that. So kinematics is just stuff that you could figure out from a videotape if you had a room with, you know, a gridded out room where you could measure anything carefully or whatever. We're not worried about masses. We're not worried about forces, just describing the motion. And this is primarily a relationship between time, position, velocity, and acceleration. And what about the 1D part? Well, one-dimensional doesn't actually have to be along a line. A one-dimensional motion is just a motion where you can either go this direction or that direction at any instant. You only have two choices of where to go. So like if a bug's on this whiteboard, they have infinitely many choices of where to go. They can go that way, that way, that way, you know. But if a bug is walking along a wire or a line, a wire that's in the shape of a line, it can only go that direction along the wire or that direction. Okay, so that's what one-dimensional means. We're only going to do cases where things are moving along a line. So I'll write that here. But we're talking about having only two choices of direction. Don't take the second choice of direction on the freeway. I mean, I guess you can get on the other side of the freeway. Okay, yeah. Okay, yes. That's just like a public service announcement. It's very dangerous. Okay, and the fact that in one dimension you only have two choices of where to go means that we can represent direction with positive and negative. Okay, so that's really convenient. And so things that we measure that have directions in 1D, that direction is represented by, is it going in the positive direction or the negative direction? Okay. Well, we're going to want to do calculations eventually that happen along a plane, or we're not going to do 3D, but it philosophically or whatever, it's no different than 2D. The problem is, in those cases, we don't have two choices of direction to move in. We have infinitely many. So we're going to need a new way to represent direction. Plus and minus won't do it anymore. And so the third topic we're going to get into is vectors. That's just purely a mathematical topic. And before we can do that, we have to go through a little introduction to trigonometry, you know, just sort of the basics of trigonometry. Yep. And then what is it about vectors that's useful in physics? What's useful is vectors give us a way to represent direction in 2D and 3D. Okay. Okay, so positive and negative won't work anymore. But vectors are going to be our new way to represent quantities that have direction. And to visualize a vector, you can think of it as just an arrow. And this arrow has two properties. It has a length and it points in a direction. Now that we've defined vectors, the fourth thing we can get into now is two-dimensional kinematics of a particle. So 2D particle kinematics. So we're still not going to be concerned with the orientation of the object we're tracking. An example of where that would be useful is if, like, physicists are trying to figure out where, a baseball player hits a home run ball. They're trying to figure out where that is going to land, or where it did land, or whatever, where it would have landed if it didn't hit the seats. They're doing the physics of this ball without caring about the orientation of the ball. So they want to know that it lands 450 feet away. They don't care about whether when it hits the ground, the Rawlings symbol is down or up or whatever. That doesn't matter to them. So they would represent this as a particle. Yep. Yeah, when they give you distances and stuff, yeah, that's how they're doing it. Yeah. So we're still not concerned with orientation. We still are just describing motion without causes. The only thing that's different now is that we're talking about objects that can move in infinitely many directions, anywhere in a plane. So the direction can be anything within a plane. And we're still dealing with relationships between time, position, velocity, and acceleration. What's different now is that these three, position, velocity, and acceleration, are going to be represented by vectors. Okay. So after we've gotten into two-dimensional motion, yep. No, the tests, I just chose dates for the test, and so it covers whatever we've gotten to at that point. The things go faster, slower based on, there's a lot of factors. So, okay, so after we've gone from one-dimensional kinematics, describing motion, to two-dimensional kinematics, now for the first time, we're going to bring the causes of motion into it. So the fifth topic is particle kinetics. I have no idea. You could have chosen any word for combining kinematics with causes, and you choose the word that's most similar to kinematics, like just to make it confusing, as far as I can tell. I didn't get to choose those words, so that's just how it is. But yes. Mm-hmm. Yeah. That's right. Yeah. Yeah, let me draw it up here. So if you have, so one-dimensional motion this particle is moving along like a wire, and we can call this direction positive and this direction negative, and those are its only two choices. But if it can move anywhere along the board, and you call this positive and this negative, it could also go here and here, and now positive and negative don't help describe it, you know. Okay, so particle kinetics means combining kinematics, the description of the motion, with the causes of the motion, and what I'm going to call the causes of the motion are mass, force, later on energy. We won't start out with that, but so now we're going to particle kinetics. Oh, this is also in 2D, so we're not going back to 1D for this. Yeah, that's right. And the first thing that we're going to talk about is free body diagrams. And free body diagrams show all the forces acting on your system, the system that you're analyzing. And the types of forces that we're going to be dealing with are the weight, that's the force applied by gravity. Pushing forces, pulling forces, and friction. And every force we're going to deal with falls into one of those categories. Then after we've talked about free body diagrams, we're going to get into Newton's laws. And you can think of Newton's laws as relationships between the motion and the causes of the motion. And the laws that we're going to talk about are Newton's second law, that's the most important equation in this class, and you've probably heard of that one before. That's F equals ma. And the second one we're going to deal with is Newton's third law. And that's the one that says, you've probably heard of this before too, although applying it accurately can be a little tricky, but it's the one that, like in the original text, is something like every reaction has an equal and opposite reaction. Yeah, we are. We're too good for the first law. The first law is like a warm-up law. Uh, it's actually, so intuitively, it's a really useful thing, and we'll talk about it in lab. But as far as calculations go, it's totally contained in the second law. You know, the second law includes the first law and a bunch of other stuff, so this is all we need for calculations.
Where would E equals mc squared?
So everything that we're doing, and I suppose everything that you would do in physics too also is called classical physics. That's before you get to what they call modern physics. Around the turn of the 20th century, some experiments came out that showed that, like, at the turn of the 20th century, around 1900, a lot of people thought physics was about to be over, you know, like everything had been solved. And then there were a couple of experiments that caused all this chaos. Yeah, let's see, what were they? Well, the first one was they found out that light doesn't, so no matter which way you measure the speed of light, even though the Earth is spinning or whatever, no matter which way you measured the speed of light, you got the same speed. Like, how could that be if the Earth's spinning one way and not the other one? You know what I mean? Like, if you're on a train and you throw a baseball this way, someone on the ground measures it as going faster than if you throw it this way. You know what I mean? But light always stays the same. Oh, that's weird. Like, maybe there's a simple explanation for that. Nope, not simple. And then, yeah, what was the, so there were a few, and that led to relativity. That's Einstein's relativity came from this experiment that's like, oh my gosh, like light seems to go the same speed no matter what the observer is doing, you know? And then the second one was that the spectrum of light coming off of a heated up body wasn't a continuous distribution of colors. It was only certain combinations of colors. Like, oh, well, maybe there's a simple explanation for that. Nope. That led to all of quantum mechanics. So relativity and quantum mechanics are what people call modern physics. And what you're studying in physics 1 and 2 are what people call classical physics. That's modern. That's Einstein, and that's modern physics. That's relativity. Yep. Okay, so Newton's third law. And then the last thing that we're going to do after Newton's laws. So the big overall topic here is 2D particle kinetics. And we're going to talk about circular motion. And the advantage that we get in circular motion is because we know something about the motion, we know it's moving in a circle, there's stuff we can say, additional things we can say about acceleration. And so we have some additional tools for calculations. So this is overall topic 5. And then topic 6 is conservation laws. And we're going to talk about 2 conservation laws. The first one is conservation of linear momentum. And one thing that is going to start to come up about now is this is going to be the first time that we can look at a problem and consider two possible directions to go, you know? And sometimes it can be tricky to know what approach is going to be the best approach. Conservation of linear momentum, though, is really easy if you remember that this is only useful for collisions and explosions. If you're dealing with any problem involving collisions of things or explosions of things, this is what you want to use. If you're dealing with something else, then this isn't going to be very useful to you. So this is good for collisions and explosions only. Those aren't the only thing that it's true for. It's just not very useful for other stuff. And the second conservation law is conservation of mechanical energy. So conservation of energy overall is a universal law. This is not exactly conservation of energy. We're going to see that under certain conditions, the only things that change are mechanical energy of the body that you're analyzing. And if those conditions hold, we can apply this, okay? But if you're dealing with things where temperatures are changing or then there's other changes in energy besides mechanical energy, and you can't use this, but we'll talk about that. And when is it possible to use conservation of mechanical energy? Usually this is useful if you're looking for a relationship between position and speed. And then the last topic in this class is rigid body motion. And this is the first time in the whole class that we're treating things as more complicated than a particle. Now, finally, we can do calculations involving changes in orientation. Or we can take changes in orientation into account. Okay. So if you're doing calculations where the orientation does matter, say you're doing a calculation related to like a football player or something, you know. If you treated a football player as a particle, then it wouldn't matter whether somebody hit his legs and someone from behind hit his shoulders, because the orientation doesn't matter. So if you rotate it, it wouldn't change anything. But that's not really how people are, you know. You can keep running if you stay on your feet. If someone hits your legs and someone hits your shoulders and you rotate your face down to the ground, then the play's over, you know. So if you're trying to figure out what's going to happen in an instant of a football game, it doesn't make any sense to treat players as particles, you know. You want to know how that orientation is going to change. after this collision, is their head going to be up or is their head going to be in the grass? Those are different. Okay. And that's pretty much the class. If we have extra time at the end, there's some other things we can get into, but usually we don't. So anybody have any overall questions about the layout of the class? Oh, yeah. Yeah, well, oh, rigid just means that it's not, we're not treating it like it's going to bend. So, like, if you're doing a biomechanics calculation, so say you're doing that football calculation, you wouldn't deal with the complexity of, like, in most cases, I suppose there are applications where you would, but you wouldn't deal with the fact that the bones, every time you do something, are flexing a little bit or whatever. It's such a small amount. You'd tend to just say, like, this part of your arm is one rigid thing. This is one rigid thing. It simplifies a lot of the calculations. So yeah, we won't be talking about things that when you apply a force to them, they bend. Other questions?
Is this all on syllabus or D12?
I don't know. Well, this will be posted on D2L, the notes from today. There is something on the syllabus sort of like this, but not in this much detail. But so as I go through the class, I'm gonna pull up this outline and I'm gonna say, okay, we are here, when we switch to new things, and I'm hoping it'll just sort of help keep kind of an overall sense of how things fit together. Yeah. Oh, yeah. Conservation in any science just means things stay the same. So, like if you, it means something sort of different than in everyday language in a way. I mean, because you think of someone who's like a conservationist going out and planting trees or whatever, but that's not conservation if you're planting more trees, Conservation just means the thing stays the same all the time. So under certain conditions, whoops, that we'll talk about when we get to this. If you add up all the linear momentum of all the things in your system before the collision, it's the same as the total linear momentum after the collision. So that's what it means. The linear momentum is conserved. It stays the same even though this collision happens. And same thing with conservation of mechanical energy. At instant 1, the mechanical energy is the same as at instant 2. Anything else? Okay. I mentioned last time that one of the things that makes physics 1 different from physics 2 is that in physics 1, you sort of have intuition that colors the way you understand these things. Most of the time, that's really helpful. You know if you throw a ball, it eventually comes down to the ground, and that's true. It does. But some of the things that you think for most people, turn out not to be true. And that is hard because for however many years you've understood it to be that way, your brain's been reinforcing this idea that we have to sort of undo and correct. And so as we go through this class, there are 4 big misconceptions that I'm going to, when we get to them, I'm going to bring them up and we're going to try to identify that part of the brain and take that out and put in the good stuff. So common misconceptions. And okay, so I'm going to tell you what's really true, and most people, in maybe not in every case, but in some cases, would be surprised that this is true. Okay, so the first one is gravity does not make heavy things fall faster. Gravity does not make heavier things fall faster. In the cases where a heavier thing does fall faster than a lighter thing, and there are cases like that, it's not gravity that does it, it's just air resistance. Okay? So that's just a difference in how the thing reacts to air resistance. That's right, it is not. And this isn't just like, you know, lay people or whatever who have this intuition. It was actually, I mean, in terms of like when physics ideas came about in history, it's pretty recently really that people understood how this really worked. Like some of the, you know, great physics people in history, Aristotle, that's the one that comes to mind right now. But I mean, that's a name, you know, that's a pretty smart guy. But he had this totally wrong. It just, you have a lot of experience that says if you drop something heavy and something light at the same time, the heavier thing is going to hit the ground faster. It's not gravity that does it, though. It's just that in those cases where it does happen, air resistance affects the lighter thing more. Yeah. Oh, yeah. Yeah. So, yeah, mass, think of mass as an object's resistance to having its velocity changed. Okay, like resistance to acceleration. Something that's really easy to shake back and forth fast has a small mass. And something that's hard to shake back and forth fast has a large mass. And the reason that it's confusing, that those two are easy to confuse, weight and mass. Okay, so before I say that, so imagine now you go into outer space, okay? You're far enough away from planets and stuff. This doesn't really happen. But let's say you go so far out into outer space that you're weightless. Okay. Well, it does kind of happen, but that's not why astronauts are weightless when they're in spaceships, and they're not really weightless. They're really in free fall as they sort of fall around the Earth. But let's say that's not what's happening. You go way, way out, far away from any planets or whatever, and you're really weightless. Okay. If you position yourself on a bathroom scale in outer space, the bathroom scale will say that you have zero weight. You're not applying any force to the scale. Okay. But if someone applies known forces to you and tries to shake you back and forth, your mass is still exactly the same as it is now, as it is on Earth, you know, on the surface of Earth. So mass is something that's a property of an object, no matter where they are. Weight is just how hard gravity is pulling on you. Okay.
That's why weight contains gravity on planets.
Yeah, exactly. So on the moon, you still have the same mass, but you have a different weight.
So how do you measure mass?
That shaking back and forth thing is literally how they measure the mass in outer space. They have a machine that shakes you back and forth and tells you what your mass is, because, and the reason they need to know that is because it's easy in outer space to learn to lose bone density. So they need to make sure people's weights aren't changing drastically, their masses aren't changing drastically.
Why did it lose bone density?
Let's exercise because they're not having.
Yeah, right. It's just like the loading on on your bones is so different that they're not getting, you know, like constantly cells in your bones are like sort of eating pieces of bone away and rebuilding that bone in ways that that are more appropriate to the way you're applying forces to your bones, you know? And so if you're not applying forces to your bones, they'll eat it away and then just use that energy in other ways, and you get, you know, osteoporosis or whatever. Apparently, I'm not an expert on that, but
There was a case study made for astronauts.
yeah,
You just have to lay there and running through stuff, not
yeah,
doing
yeah, right. And so it turns out that measuring their mass is really important, and they do it with these shaking. I don't know what it looks like, but I know that's the idea of it. Shakes you back and forth to measure your mass. But I was going to say the reason that it's easy to get mixed up between whether you're talking about weight and mass is because on a given planet, on the surface of like in a given location, weight is proportional to mass, you know? So somebody who has twice as much mass also weighs twice as much on Earth, weighs twice as much on the moon, although they're different weights, you know? And that's why you're, okay, and it's also confusing because your bathroom scale, if you flip it over, has a setting and you can choose whether you want to weigh yourself in pounds, which is a measure of weight, it's a measure of force, or kilograms, which is a measure of mass. And so they seem like interchangeable, but your scale is really measuring your weight. It's pretending, it's saying it can measure your mass because it's assuming that you're measuring yourself on Earth.
So like one time in the lab, you measure some grams,
When you measure, okay, so when you use like what's that kind of scale called? The scientific scales, the balance scales or whatever. Okay, you can, so you put like a gram over on this side, and you put something over on this side to see if it's a gram. You really are, I guess, you're using gravity as sort of an intermediate way to measure the mass of that thing, because whether you were on the moon or Earth or wherever, if this thing balances, their masses are the same. And it doesn't matter what the strength of gravity is, you know. This is getting deep into the weeds. But we'll talk about that more as it comes up, but it is funny. So a bathroom scale it doesn't measure your mass. All it's measuring is the force, sort of indirectly, that gravity applies to you, and that's the weight. Okay, so gravity does not make heavier things fall faster, and well, that's pretty easy to see if you imagine like a 200-pound person falling out, not falling, out of an airplane with a parachute on versus like a small half-pound lead ball being dropped out of the airplane. The lead ball is obviously going to hit the ground faster. That's so the man parachuter with the large mass is not being pulled faster by gravity. We'll see examples of that. The second common misconception is that an object's horizontal motion does not affect gravity's ability to pull it down. So if you gently throw a baseball, you know it follows sort of a curved path, okay? And that curve is a parabola. If you shoot a bullet out of a gun, it's pretty common intuition for people that it's going so fast that it doesn't curve at all, it just goes straight. Well, the curve isn't very exaggerated, because by the time that ball dropped this much, that bullet's already way out of your vision. But if you stand here and shoot a bullet horizontally, and you have enough room for it to, there's no walls there, and you have a couple 100 yards, it'll hit the ground in exactly the same amount of time it would have hit the ground if you just released it like that. Okay, so people have this sort of natural sense that the faster something is moving horizontally, the less gravity pulls on it somehow. That's not true. It's just that if it's going really fast, you don't see it hit the ground. You don't see it drop because it's out of your vision. Yep. Yeah, that's right. Yep. We'll do some calculations related to that later on. Yeah.
Have you seen the movie?
Nope.
Well, like it's a mile-long shot, and like they show it with the stove.
Yeah.
They put it like right on the guy's head. Like I was listening to the comic and they're like, they have to be like
Yeah.
a good 10 feet.
Oh yeah, right. Exactly. That's the same idea. Yeah. Yes. Exactly. Yep. Third common misconception. In any collision, actually any time two objects are in contact, the objects actually apply the same size forces to each other. That's Newton's third law. And so think about what that means. If you have a collision where something doesn't seem to be affected very much and the other thing is affected a lot, like a baseball bat hitting a baseball or something, it's very natural to think that the bat is applying a really big force to the ball and the ball is applying a much smaller force to the bat. But it's actually not true. The difference in the way the things behave due to the collision really just has to do with how that force affects each thing. So say that there's 1,000 Newton force, magnitude force of 1,000 that the bat applies to the ball and the ball applies to the bat. Well, if you apply 1,000 Newton force to a bat that's being held by two hands, that's connected to a 200-pound person who's wearing cleated shoes and connected to the ground, it just doesn't affect that bat's motion very much. But if you apply 1,000 Newton force to a, few ounce baseball, it goes flying, And so that's all it is. These collisions, even in collisions where it seems like there's a winner and a loser, it doesn't have anything to do with what force is applied. Okay. Yep.
Could you give an example,
Yeah.
the highway on the car?
Yeah. So when a mosquito hits the windshield or whatever, a bug hits the windshield, the force, the bug applies, let's say, I have no idea what the force is, but let's say 20 Newtons of force to the window. And the window applies a force of 20 Newtons to the fly. But 20 Newtons is a lot of force to be applied to a fly. Its body can't take anything close to that. but a windshield can take a lot of force, and then that's the difference. So one gets smushed and one, it has no problem, you know.
So it has to do with the mass of the object.
Yeah, that's right. Yep. And just the structure of the object, you know, some things will break and some things won't. So like in a boxing match, someone gets punched in the face and gets knocked out. During that collision, the glove applies 1,000 Newton force to the face. The face applies 1,000 Newton force to the glove. It's just that that glove is designed to take big forces and your face isn't, you know.
So the person, or not the person, but the item that basically dictates the amount of force is the person.
They sort of both do together, really.
Together.
Yeah. Like, for example, if, so say somebody, you know, like a karate expert or whatever, they can punch like a sensor and apply like a big 2,000 Newton force, some big force, okay? But now, like, if they punch this piece of paper, no matter how hard they swing, they can't apply 2,000 Newtons of force to this paper because it just bends away, you know? So it really is both of the two things together that determine how strong the force is. Okay, one more thing. The last common misconception is in 2D and 3D, things can accelerate even if the speed isn't changing. So like if you're in a car and you take a really sharp turn, even if you don't change the speed of the car, that feeling in your stomach is acceleration. And the reason for that is turning is a kind of acceleration, produces acceleration, just like speed changes do. And this is a hard one to get used to because I think the main reason is in everyday language, acceleration means changing the speed. But in physics, acceleration means the velocity is changing, and velocity has direction. So if you're going 50 miles an hour that way, and a second later you're going 50 miles an hour that way, there was an acceleration because you changed the direction that much. Okay, so keep these 4 things in mind, and I'll bring them up when we get to these topics. But these are the things that we're going to try to like correct in your brain. Any questions about any of those? Okay. Well, the lab tonight is the same as it was on Monday. It's just an intuition pre-test. It'll only take half an hour, and once that's over, turn it in, you can leave. But let's wait to start it at 7:30 in case people are showing up. So I'll hand it out and stuff at 7:30.